Now let's talk about how the colligative properties will change when we have a solute that is ionic. Previously, we were dealing with non-ionic, non-volatile solutes, so the concentration that was prepared with a non-ionic solute was identical to the number of particles in solution. But when we're dealing with something that's ionic, the number of particles in solution will be different from the actual prepared concentration. Recall that an ionic compound is made up of a nonmetal and a metal together. For example, if we have sodium chloride, which is a solid ionic compound, and we dissolve it in water, it doesn't stay together as a sodium chloride unit. Instead, the particles dissociate, and we get sodium ions that are aqueous, plus we get chloride anions that are aqueous, meaning those ions are surrounded by water. In theory, we should get two particles when sodium chloride dissociates. Compare that to a salt like magnesium chloride. When we dissolve something like magnesium chloride in water, it breaks up into a magnesium 2+ ion, plus we get 2 chloride anions per formula unit of magnesium chloride dissociating. That's due to that subscript 2 right there. So in theory, when one formula unit of magnesium chloride is dissolved in water, we should get 3 particles by adding up 1 for the magnesium 2+ ion and 2 for the chloride anions. Now, the theory number of particles is not exactly how many we'll really see. It can change depending upon the substance. Most of them do not dissociate to 100%. Some could be close. So that number of particles we're talking about in theory is just an estimate. And we'll talk about this a little bit later, but it's due to a phenomenon known as ion pairing. When an ionic compound is dissolved in water, it produces something known as an electrolytic solution, or the ionic compound is an electrolyte. An electrolyte is a substance that will produce an electrically conducting solution when it's dissolved in something polar, like water. This is because, as we saw, the ionic compound will separate or break up into its cations and its anions, and since it's ionic, it can conduct electricity. Many of the common sports drinks, such as Gatorade or Powerade, contain electrolytes. Common electrolytes that the body needs are things like potassium, chloride, sodium, magnesium, calcium, so they contain ionic salts that have those ions within them. The apparatus in the lower right corner is called a conductivity meter, and a conductivity meter is something to allow us to tell if a solution is an electrolyte or a non-electrolyte. The bulb on top can be very bright, or it can be dim, or it cannot be lit up at all. If you were to put a conductivity meter into a solution of an electrolyte, the bulb will shine very brightly as the circuit will be complete. If it's in a weak electrolyte, the bulb will turn on, but it will be very dim. If it's in something that does not conduct electricity, such as a non-electrolyte, the bulb will not turn on at all. So let's talk about what strong, weak, and non-electrolytes are. A strong electrolyte is something that will fully dissociate or ionize in water. They are good conductors of electricity. An example is a strong acid. So let's use HCl as our example. Hydrochloric acid is a strong acid that when it's put in water, it will ionize and form hydrogen ion, and it'll form chloride anion. It's going to ionize 100% so that in the solution, all that's present is H+ and Cl-. There will not be any combined molecular HCl in the solution anymore. This is due to it being a strong acid. The definition of a strong acid was an acid that ionized 100%. So if you put a conductivity meter in a solution of HCl, the bulb is going to shine very brightly. A weak electrolyte, on the other hand, is something that only partially ionizes or dissociates in water. These are weak conductors of electricity. An example could be a weak acid, such as acetic acid. If you put acetic acid in a solution, it's going to break up a little bit into its ions. You'll get a little bit of H+ and you'll get a little bit of acetate anion, C2H3O2-. But most of the acid is going to still remain combined as molecular HC2H3O2. So therefore, we used double arrows to represent the equilibrium of a weak acid. Weak acids only ionize to a small extent, so most of it will still be combined, and if you put a conductivity meter in this solution, the bulb will turn on a little bit, but it will not be very bright because there's only a small amount of ions in solution. A non-electrolyte is a substance that does not dissociate at all, so it will not produce any ions. How you can identify a non-electrolyte is look for compounds of carbon or organic compounds. This is going to be a non-conductor of electricity. An example could be sugar, C12H22O11. Sucrose is a solid compound, and when you dissolve it in water, it does not ionize at all. It'll just become aqueous sucrose molecules that will be surrounded by the water molecules, but it's still combined as a molecule. Therefore, this will not conduct electricity at all because there's no ions produced. You want to look for compounds that contain carbon, hydrogen, oxygen, nitrogen, things that are in the upper right-hand corner of the periodic table, non-metals. These are going to be molecules that do not break up. Here's an example comparing what the conductivity meter would look like in solutions of hydrochloric acid, acetic acid, and ammonia. In the first one, in HCl, we can see at the molecular level, all that's present is hydronium ions, which is equivalent to a hydrogen ion, and chloride anions. There is no combined HCl in this solution due to it being a strong acid. So the bulb on the conductivity meter is shining bright because this is a strong electrolyte. In the middle, we have acetic acid. Acetic acid is a weak acid. If we look at what's present at the molecular level, there's a small amount of hydrogen ion and a small amount of acetate anion. So the bulb does turn on a little bit, but it's dim. Mostly what's present in solution is combined molecular acetic acid. That's the majority of it. So since it's a weak acid, it's going to be a weak electrolyte. On the far right, we have NH3. NH3 is ammonia. This is a weak base. In water, ammonia will ionize and form a little bit of ammonium ion and a little bit of hydroxide anion. So once again, we have a small amount of ions present, but mostly what's present is the molecular form of ammonia, NH3. And NH3 is not an ion, so we only have a very small amount of ions. So since it's a weak base, it'll also be a weak electrolyte. The light is on, it's a little hard to see, so it's very dim. This just gives you an idea of what's going on at the molecular level or what's swimming around in these solutions that will either conduct electricity really well or not conduct electricity well. This is a flowchart that will help you determine if a compound is a strong, weak, or non-electrolyte. The first two categories that's broken up into is ionic compounds versus molecular compounds. Recall that ionic compounds are composed of a metal plus a nonmetal, whereas molecular compounds are nonmetals combined with other nonmetals. We learned the solubility rules for ionic compounds last year. If a compound is ionic and soluble, meaning it will dissolve, it's going to be a strong electrolyte. I know we don't have the solubility rules right out in front of us at this moment, so let's just assume if we see an ionic compound that it's going to be soluble. Molecular compounds are a little more complicated. If we have an acid and that acid is strong, so we learned 7 strong acids last year, it's going to ionize 100% and therefore it will be a strong electrolyte. If the acid is one of our acids that's weak, it's not one of our 7 strong acids, it's going to ionize to a small extent and it'll end up being a weak electrolyte. Same idea with bases. If it's a strong base, such as something that contains a metal and a hydroxide anion, it's going to ionize completely and it'll be a strong electrolyte. One of the only weak bases we talked about last year was ammonia, or NH3, and we saw in the previous slide that that'll conduct electricity very weakly, and it was a weak electrolyte. And under the molecular category, you could have something that's not an acid or a base, but it's a compound of carbon, hydrogen, oxygen, nitrogen. It contains those nonmetals, and those are going to stay together as a molecule and be a non-electrolyte. Determine if the following are strong, weak, or non-electrolytes. Starting with NaClO3, this is sodium chlorate, and so we have a metal with a nonmetal. The nonmetal happens to be a polyatomic ion. And since this would end up being a soluble ionic compound, it's going to also be a strong electrolyte. HBr, this would be hydrobromic acid. This is one of our strong acids, and so it'll ionize 100% into hydrogen ion and bromide anion. This would also be a strong electrolyte. HF, this is hydrofluoric acid. This is not one of our 7 strong acids. Therefore, we assume if it's not one of our strong acids, it's a weak acid. And since it's a weak acid, it'll only partially ionize, and it'll also be a weak electrolyte. Magnesium chloride, this is an ionic compound, metal and a nonmetal. And so we'll assume it's soluble, and therefore it'll end up being a strong electrolyte. C6H12O6, this is glucose. Notice that we have all nonmetals together, and so this would be a molecule. It contains carbon, hydrogen, and oxygen, and it's not going to ionize at all. This would be a non-electrolyte. KOH, or potassium hydroxide, this is a strong base. It's also an ionic compound, so it'll ionize into K plus and OH minus, and it'll be a strong conductor of electricity. Methanol, CH3OH, all carbon, hydrogen, oxygen. It's going to be a molecule, so it's not going to ionize at all. It'll be a non-electrolyte. And sulfuric acid, H2SO4, that was one of our strong acids, so this will also be a strong electrolyte. The Van 't Hoff factor, or what I like to call the I factor, tells us how much something has been dissociated in solution. Usually compounds that we say are soluble don't always dissociate 100%. So the I factor tells us how much it actually does dissociate, the extent of that dissociation. I is equal to the moles of particles in solution divided by the moles of formula units dissociated. So for an ionic compound, imagine we have sodium chloride. If we have 1 molecule of sodium chloride, this represents 1 formula unit. So the denominator would be the molality or the molarity that we think we create the solution to be. And the numerator would be how many particles are actually present in solution. We're really not going to calculate an I factor, but we want to use the I factor in our colligative property formulas in order to change them for ionic compounds. So if we rearrange that formula and we solve for the moles of particles in solution, the real true number of particles, that would be equal to the I factor times the moles of formula units dissolved. So anywhere in our colligative property formulas where we have moles of solute, if we multiply by that I factor, we can adjust the formula to be for an ionic compound. Now I mentioned that the I factor in theory might not be exactly equal to the true or actual I factor. So for sodium chloride, if we had 1 formula unit of that, it would break up into a sodium ion and a chloride anion. So we would say in theory that 1 formula unit of sodium chloride would produce 2 particles, or an I equal to 2. Now the real life I factor for sodium chloride is close to 2, but it's actually only 1.9. This is due to something known as ion pairing. In solution, most of the chloride anions, which are negative, are going to be surrounded individually by the water particles. They'll be surrounded by the partial positive charge on the hydrogen ion we learned. Most of the positive Cations, whether they're potassium or sodium, those are going to be surrounded by the partial negative charge on the oxygen water molecules, so they're completely separated from one another. But every now and then, there'll be a particle of potassium chloride, sodium chloride, whatever ionic compound you're looking at, where the cation and the anion will still be butted up right next to each other and not completely dissociated. That's an ion pair, and that's why the I factor does not always equal the number of theoretical particles. So in this case, that ion pair is surrounded by water molecules, but it's still connected together, so it's not fully dissociated. You're usually not going to know the actual or the measured I factor for a different electrolyte, so often for problems we'll end up using the predicted number for the I factor. If the problem does tell you the true or measured value for the I factor, you can go ahead and use that. But let's look at an example here. HCl breaks up into H plus and Cl minus, so we predict it forms 2 particles, but in reality, the I factor is 1.9. Or if we look at something like magnesium sulfate, that should break up into magnesium 2 plus ions and sulfate anions, so we predict 2 particles. But the ion pairing is really strong in something like this, so the actual measured I value or I factor is only 1.3. There's no way you would know that value unless it was given to you. Something like iron 3 chloride, that's going to break up into Fe3 plus, and then you're going to get 3 chloride anions per formula unit, so a total of 4 particles. We would assume the predicted I factor is 4. In reality, though, it's only 3.4 due to ion pairing. Anytime you have a non-electrolyte, something with carbon, hydrogen, oxygen, like glucose, we're going to end up seeing that it breaks up into only 1 particle overall. So the I factor is always going to be equal to 1 for a non-electrolyte. Now let's see how we can modify all of our colligative property equations to take into account the I factor for a solute that is ionic. First, we have Raoult's law, which said the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. In this case, the moles of solute is in the denominator, so we're going to multiply that moles of solute by the theoretical I factor. Unless we know the actual I factor, then we could use that as well. For freezing point depression, molality is in the numerator, so moles of solute is in the top. So we're going to end up just throwing the I factor out front and multiplying by it. Same thing with boiling point elevation. Delta TB equals IMKB. We multiply by that I factor. And for osmotic pressure, pi equals MRT, while molarity is moles of solute per liter of solution, so moles is also in the numerator, so we just have to multiply by our I factor. The only one where it's in the denominator is Raoult's law. The rest of them, we just throw the I factor out front. And it's going to affect the colligative properties because we're going to have a greater number of particles in solution. So for example, the vapor pressure will drop even more if we have an ionic compound, or the freezing point will be depressed even greater. The boiling point will rise even more, or the osmotic pressure will be greater. What is the vapor pressure in millimeters of mercury of a solution made by dissolving 18.3 grams of sodium chloride in 500 grams of water at 70 degrees Celsius, assuming complete dissociation? The vapor pressure of pure water at 70 degrees Celsius is 233.7 millimeters of mercury. So notice when you're reading these problems and they're all mixed up that you got to be really careful. In this case, I'm trying to hint to you by underlining NaCl that NaCl is ionic. So we know that it's going to break up into particles. We're going to get sodium and we're going to get chloride anions. So our theoretical I factor in this case will be equal to 2 if we assume complete dissociation. Our formula that we're going to use since we're talking about vapor pressures is Raoult's law. So it's still the same formula overall. The vapor pressure of the solution will equal the mole fraction of the solvent times the vapor pressure of the pure solvent. But when we break that down, we're going to end up with moles of solvent over the I factor times the moles of solute plus the moles of solvent times the vapor pressure of our pure solvent. So let's do some conversions. We have to get our mass of sodium chloride into moles, and we have to get our mass of our solvent water into moles in order to be able to calculate the mole fraction. So we have 18.3 grams of sodium chloride. Using the molar mass, 1 mole of NaCl is 58.5 grams. That gives us 0.313 moles of sodium chloride. We have 500 grams of water. The molar mass of water is 18 grams per mole. That gives us 27.8 moles of our solvent water. And now we're going to plug everything into our modified Rayleigh's law. The vapor pressure of the solution equal to our mole fraction. Our moles of water are going to go in the numerator because that's our moles of solvent, so 27.8 moles on the top, times our I factor for our solute, 2, and our moles of solute was 0.313, plus our moles of solvent, because it's total number of moles in the denominator, so 27.8 moles, times the vapor pressure of our pure solvent. We were told in the problem that the vapor pressure of water was 233.7, so that's our pure solvent. Millimeters of mercury are our units. Mole fractions unitless, so our vapor pressure will also be in millimeters of mercury. And that should come out to being lower than our vapor pressure of our pure solvent, and that is 22.86 millimeters of mercury. So vapor pressure lowering. In this case, it's lower than it would be if we had a non-ionic compound because it wouldn't dissociate into particles. So our I factor would have been 1 for something that was non-ionic. What is the freezing point of an aqueous 0.106 molal magnesium chloride solution? Assume complete dissociation. So once again, we have an ionic compound, we have a metal and a nonmetal. So magnesium chloride, when in water, will dissociate into magnesium 2+ ions. Those will be aqueous. Plus, we're going to get 2 chloride anions. So our theoretical I factor in this case, we got 1 magnesium ion, 2 chloride anions, is going to be 3. We're figuring out a freezing point, so we're going to want to use our freezing point depression formula. Delta TF equals I times M K sub F. And we're in an aqueous solution. So aqueous means in water. The freezing point depression constant, K sub F for water, is 1.86 degrees C per molal. So that's a constant that you can look up. Plugging in here, we have our I factor as 3. Our molality is what we think we made this solution up as. We made it up as a 0.106 molal solution. Times our K sub F, 1.86 degrees C per molal. You can see that the molality will cancel and we'll be left with units of degrees Celsius for our delta T sub F. And so we end up getting, for our change in our freezing point, 0.591 degrees Celsius. Now that's not our actual freezing point. Our actual freezing point is taking the freezing point of the pure solvent minus the delta T sub F, because that's how much it's going to drop by. And so since our pure solvent is water, that would be 0 degrees Celsius minus our change in our freezing point, 0.591 degrees Celsius. So our final freezing point is negative 0.591 degrees C.